All right, for those of y'all who are watching now, I'm sorry you didn't get to, yes, you can get extra credit. You have to remind me though. Shoot me an email or something. For those of y'all who are just paying attention now, I haven't said anything of consequence besides why I think vision's so cool. All right, yes, so the electromagnetic spectrum, visible light ranges from 400 nanometers to 700 nanometers. And so when we're talking about vision, we're talking only about this small component of the electromagnetic spectrum.
Is there another term for the light waves? Like I said, there was infrared and ultraviolet. I mean, are they ones like light waves, or like, or is there like a certain name for those particular waves in that spectrum?
Like a different label than infrared?
Oh, are they considered infrared?
Yes.
Oh, okay, okay.
Yeah, yeah. That's the infrared spectrum.
Okay.
In there. Yeah. And so when you have things like night vision goggles, it's essentially taking infrared reflection off of the Earth and transferring it into essentially the visible spectrum. Come on, where'd you go? There we go. So when we talk about things like brightness, what we mean is it's just a function of the luminance values of a material. So dark colors appear dark because they have higher absorption of that energy. Lighter colors tend to absorb less and are reflecting a greater proportion of that light. And so this is why in the god-awful months of July and August down here, black cars get so much hotter than ones with like tan interiors, because instead of reflecting that energy back out, it's absorbing that energy and re-radiating it as infrared. Yes, you're exactly right, Dennis. So, if you take a look here at the bottom 4 squares, on the inside, the smaller square of each one of these will probably yield a different percept to you, right? The inner square on the farthest left looks to be lighter than the inner square on the farthest right, although there's a little bit of a washout here, so it's a little less compelling on the overhead projector. But in reality, they're all the same reflectance, all the same luminance. And so what we're relying on is this contrast of the border to provide our phenomenological experience of color. And the visual system is replete with examples of evolutionarily advantageous adaptations our system has made to make us really good at surviving, right? We're really good at contrast because what matters is not really the absolute value of that reflectance or that brightness. What matters is what's different from the surrounding, right? And based off of that difference, we're now going to amplify those. And so we have specific receptors in our retina that process information at these borders very differently based off of how light or dark it is to give you a compelling percept that these inner squares are different colors. I'm sure you all remember years ago this dress example, right? Kind of took the internet by storm. I see it currently as black and blue. I think you can also see it as white and gold. But your brain is making certain assumptions about the world and then informing what color you actually see this to be. All right, and so when we go back to the electromagnetic spectrum here, we can see the discrepancy explained by what type of light is coming and hitting the dress, or what our perception or expectations of that light would be. So if I can get, come on now, ignore this, I'm just getting my pen going here. So on the red side of the spectrum is a little bit more of what the sun emits, right? It's a little bit red shifted. Fluorescent lights, on the other hand, like we have in this building here, are more on the blue side of the spectrum. And so I don't know how to spell fluorescent, so I'm going to abbreviate it with an F. So what your brain is doing is making an assumption about what type of light is hitting this dress. If the assumption is that this is natural light, like you get from the sun, it's going to subtract away the reds to try to give you a true color approximation, which results in the blue and black percept. If, on the other hand, it assumes that the light reflecting off of this is coming from fluorescent lights, it's going to subtract out that blue, giving you the white and gold percept. And I think this is a really neat example, and you may have also seen this with the Yanny versus Laurel auditory version of the dress, because it serves to illustrate your brain doesn't really care about what's out there. It cares about kind of what's going to help you survive, but what you see isn't necessarily a reflection of what actually exists, right? Your brain's making a whole bunch of determinations and calculations, not in an effort to trick you, but to make survival easier. So now let's get into the sort of anatomy associated with vision. Move this out of the way. So here is the front of your eye, and light comes in through the cornea, right? So the cornea is this outside clear part of your eye. And the cornea serves a couple purposes. One is sort of kind of to be a protective layer. So you actually have stem cells at the base of your cornea that will help regenerate the cornea if it's damaged. But it's also to refract that light. So as the light comes in, the cornea is your eye's first attempts at focusing that light. So if you've ever known somebody who had LASIK eye surgery, what they do is literally cut the cornea off, reshape it, and reattach it. So they're just changing the shape of the cornea to help with that refraction. The light then passes through into the lens here. And so the lens is this little football shape right there. And the lens is controlled by ciliary bodies. It's kind of hard to see with that color. But the ciliary bodies are attached to that lens at the very ends. And so they're either stretching or compressing that lens to change your ability to focus. And so when you look at something up close and then look at something out far, that's your ciliary bodies doing the work, right? Stretching or contracting that lens to allow you to focus, or as we call it scientifically, accommodate to that information. The light is then refracted through that lens and comes back to focus at the fovea, right? So the very back of your eye, back in here, That's where your retina is, and I'll show you what the retina actually looks like. But it takes all of the information from your retina, bundles it up into these nerve fibers, and then sends it out the back of the eye. So the fovea is the area of concentration for what we call the cones. We'll go over those in just a second. But when you're looking at something, right, when you're fixating on it, you're seeing color, we call that foveating.
I could be wrong on this, and I may remember this was something wrong, but the fovea, like when you're looking at something, so you know, like you think this, I can focus on this, but then everything else is kind of blurry. Is it like the retina, or I guess the rest of the light, or the line, I guess you say, that's not on the fovea, that's what's blurry, I guess? Yeah, so I think I'm going to go over this on one of the next slides. Let me double check real quick. Yeah, I'll go over that in just a second. That's a really good point. So this is what the retina actually looks like, right? So here is the back of your eye. Here's the front. And so that light is coming through all this material into the back. And activating either your cones or your rods. Once that information activates, either your cone or your rod, it sends the information to these horizontal, Mueller, and bipolar cells. These amacrine cells serve to highlight those differences, right, that we just showed with those gray boxes. And then it all gets bundled up in these ganglion cells and sent back to the brain. So you have this area back here, this retinal pigment epithelium. When you see animals that have reflective eyes at night when you shine a light, they don't have this RPE, this retinal pigment epithelium. And so this RPE helps serve kind of as a cleanup crew for the back of your retina. So when you've got damaged photoreceptors, it helps with that cleanup process. But one of the benefits of not having the RPE is that the RPE absorbs some of that light. And so animals that don't have that are able to get kind of a secondary chance at seeing at night because that light comes in. If it's not picked up by the photoreceptors, it's then reflected back out. And some of that information then hits those photoreceptors. And so on your eye, I'm going to draw a very crude eye here. Bear with me. Those who have taken me for S&P know how bad my drawing skills are. So here's your eye again. The light's coming in this direction, and your retina is back in there. What you see here is a topographic map of the distribution of your cones and your rods, right? So there's two different types of photoreceptors. Your rods are really good at picking up light, but not very good at spatial resolution. Your cones, on the other hand, are not that great at picking up light, but are very good at spatial resolution. Your cones are also what help you see color, right? So the rods are essentially a binary. Is there light or not? The cones are, and I'll show you in just a second, there are three different types of cones that are particularly sensitive to different wavelengths of light. And so your question about the actual blurriness of everything around you comes from the fact that at your fovea, you've got all those cones, but once you get outside of that, you have only rods, right? Or pretty much only rods, which are trying to resolve that information. And so if you've ever gone out at night and you can see a star off in your periphery and then you go look at it, it disappears. It's because in your periphery, you're activating those rods, which is allowing you to pick up the fact that there is some light there, even a little bit of light. But then the cones themselves are not all that sensitive to light. And so when you look at it, they are not activated to a sufficient point wherein they give you that experience of seeing the light. Emmanuel, mask, please. Thank you. And so you have your rods and your cones. And like I said, you've got the cones that are maximally sensitive to specific wavelengths. Right? We call them blue, green, and red, although they more correspond with kind of magenta, green, and yellow. But what you see here is that absorption rate for each one of these cones at the different wavelengths. All right, so your blue cone is maximally activated at 420 nanometers. The green cone at 534, and then your red cone at 564. And so if on a computer you've ever had to select the color for something, for a background or for lines or whatever, you may see that you have to put in that RGB value, right? The red, green, blue. That serves to illustrate kind of a real world experiment where you can show that just by varying the R, the G, and the B values, you can get to just about any color on the visible spectrum, right? Just by having activation, varying levels of activation among each one of these curves. You can see how at every point on this continuum on the x-axis, you're going to get different patterns of activation across these three cones, which sends that signal to your brain to give you the phenomenological experience of color. I'm going to pause real quick. Does anybody have any questions?
Do we need to remember those peak numbers?
You don't need to remember the peak numbers. Just kind of remember roughly that we have three and they correspond to different.
Yeah, I realized I know how to get the right peak numbers with that.
Yeah. Any other questions? TV uses the same tech with LCD and LED. Absolutely, yeah. And so this was kind of one of the early attempts to try to understand the eyeball before we actually got the imaging capabilities. You could say, all right, we're going to take two different points, and can we combine different projections of luminance with these two control knobs, essentially, to give us all the colors? No. Well, let's try three, and three gets you there. And it just so happens that that corresponds to the three cones we have, which helps inform kind of each one of those pixels on your computer. So you may be asking, what the hell does this have to do with human factors? Why should we care about this? Well, it can help inform a lot of what we consider about design. And so a question kind of came about given this sort of phenomena of something known as the Purkinje shift, which looks at our sensitivity to colors like red at low light situations, right? So you may have experienced this kind of at dusk. If you go outside, if you have roses out there, the roses are going to appear black before the grass does, right? And that's that Purkinje shift. So some experimenters decided that we're going to take a fleet of fire trucks in Dallas, Texas, and we're going to paint half of them lime green and the other half of them red. right? I'm sure you all have seen this disparate color patterns at different cities. They said, all right, let's just look at what the probability of getting in an accident was. What they found is that those who were riding in the red fire truck were about 3 times more likely to be in an accident than were those who were in that lime green fire truck. They were getting rear-ended or T-boned at a much higher rate because people weren't able to see them as well. And so this just serves to highlight the differences in those accidents. Are they? I didn't know that.
Yeah, I always heard, well, I always been told that, and I
Yeah.
think like in my car was red, and it would be higher. Just because red, I would assume because red's like, like a racy color or whatever.
Yeah.
But that's why I said it was an assumption, right?
Yeah.
But, red beans was interesting time.
I hadn't heard that. That would make sense. I mean, God, these insurance companies are running the actuarial tables on everything to make sure that they're able to get every cent they can out of you. So that makes sense. So yeah, red is harder for the photopic, so that day system, to see. But it's almost impossible for the scotopic, that nighttime system, to see. Interestingly enough, it's also really hard for computer vision systems to pick up on red. And so this helps explain some of those cases where, for example, a Tesla in self-driving mode slams into the back of a fire truck on a highway, right? It's struggling to see that red fire truck as something it needs to avoid. So again, this serves to highlight the difference wherein you have the yellow or lime green fire truck maximally reflecting 520 nanometers, whereas the red fire truck, you're at 670 nanometers or so. And these are the relative luminance, right? Your system's ability to pick up on these lights. So lime green is kind of maximally simulating this photopic system, and it's still giving you a fairly good activation of that scotopic, that nighttime system. Whereas the red is giving you very little activation in either. And I love this example because this is another instance of intuition not always being right. Right? I mean, the data I showed you is 35 years old. And how many fire trucks do you still see going around that are painted red, right? Because that's our expectation. Whoops. We think, how could you miss a big red fire truck? Well, it turns out it's pretty easy to miss a big red fire truck.
Do you know if say an evaluation or a newer version of that? I mean, because when I see things like that, I immediately think of variables, right? Maybe different drivers, this, that, and the other. Mm-hmm. Immediately, let's variables from the bottom.
Oh, absolutely. Yeah, so I don't know. I suspect there has been subsequent replications of that effect. But it's also, the effect itself is largely just representative of an anatomical kind of explanation for it. So, I mean, the anatomical explanation has been replicated many times over. I don't know about the fire trucks example, but I suspect if you were able to go out and get actual information, you know, if Birmingham had lime green ones in Huntsville, I suspect you could probably see disparate effects for that.
I
Yeah.
can't argue with science being really easy to see them red. I can't argue with that.
Yeah.
I'm just curious.
You're absolutely right about, you know, the concerns of any sort of control over it. You know, maybe those who were assigned to the red fire truck just sucked at driving.
exactly. So yeah, those are very good points. All right, so take a quick second. If you're on Zoom, you can just discuss with yourself or your cat or whatever. If you're in here, talk with your neighbor. Why might it be that we use red lights in order to avoid destroying your night vision for things like astronomy, picture developing, etc.? And then we will bring it back together and talk about it.
So do you mean like when they use night vision, do they use like the infrared lights? Is that what you mean?
Yeah, so if you ever go into like a film developing room, it's only got red lights in there, right? With the hopes that it allows you to see in the dark room a lot better than in the than if they had like yellow or green lights in there.
I don't think we know we had that. No, this.
So maybe if you don't have more separate for red light, our will be able to just the dark room.
I was gonna say, it takes time, like, to go from like a bright lit room to outside, you have to come to your eyes and adjust. I mean, for the graphic, it's just so far down and probably try to adjust.
They're red lights. You can buy the white or the ones, but then they make purple ones too. So probably worth it why that design. Because it's got nothing to do with the bulb.
Yeah, I suspect that's probably because reptiles are probably maximum sensitive to infrared. So you're probably getting any a little bit of visual spectrum.
I remember we used to buy the purple or the red ones because I could see it one night with
Yeah, there you go.
instead of
Exactly.
we had the white ones.
Yes, and I will explain why that is in just a second.
It's actually not really like they're like I don't sleep or I have her for like 8 years.
Did you really?
And so I have like a red light emergency.
That's wild. All right. So who has a guess? Yeah, Andrew.
So like when it's dark out, like your eyes adjust to the lower level of light
Mm-hmm.
in a room. So if there was a bunch of yellow light or green light or something like that, then maybe your eyes would not be able to adjust to a dark room. But if it's red, then we don't have much receptors for that. So
Yeah. So when we think about the actual visual system, again, we have essentially a breakdown of two different things, right? Our nighttime system and our daytime system. You can see that over here, where red light activates, we have almost no activation under the curve of that scotopic or that nighttime system, right? And so that now leaves kind of maximal sensitivity for other sources of light that may be coming in. And so when we think about the actual sensitivity of our system, let's say I were to shine a really bright light in your eye. You would, let's draw a graph here, and this is sensitivity. There we go. Sorry, I had to spell that one out. So as soon as I shine that bright light in your eyes, you have very little sensitivity, right? But you slowly are able to build that back up with time. That's why it takes about a half hour of being outside for your eyes to adjust to the nighttime, because you are increasing that sensitivity, because each one of these cells, after they fire, has a latency period from when they can fire again, right? And so if a whole bunch of your eyes have been, or a whole bunch of your photoreceptors have been what we call bleached, in the sense that they all fire, it becomes hard to get that sensitivity back immediately. That's why if you get a really bright flash of light, like somebody's taking a camera and you're looking right at the light bulb, you lose some of that sensitivity like immediately thereafter because your eyes have essentially been bleached. It's also the case that your brain is particularly sensitive to kind of blue light in general. And so getting any sort of blue light
coming in and hitting your retinas triggers what's known as the circadian rhythm to kind of disrupt, right? Circadian rhythm is that 24-hour sleep cycle. And so disrupting your sleep cycle with blue light makes it harder for you to fall asleep and harder to stay asleep. And that's why you'll see things on your computers and phones, like those red light filters. It's to allow red light through, but not allowing that blue light through that would disrupt that circadian rhythm. There you go, exactly. All right, so once that information comes into the retina, hits the retina, and then gets sent to your brain, it has to be processed, right? And we can think about this processing leading to perception as coming from either top-down or bottom-up origins. So bottom-up processing would be you have a stimulus out in the world, and your senses give you that information, and you slowly build that up, right? So think of this as if I walked in here and saw the chair there, but I didn't know it was a chair, I would look at it, I would see, okay, I've got 4 essentially lines or poles moving up. Now I've got a flat piece there that connects all of them. I've got a vertical flat piece that fits in with my understanding of what a chair is. So yeah, so I built it up, right, from the ground up, bottom up. The top down says I've got certain expectations of what's going on in the world. And based off those expectations, I'm able to perceive my environment accordingly. So, what does what I just wrote say? The cat, right? Even though, actually, I think I made it even harder on you. But even though these 2 letters in the middle are almost identical, your top-down expectations are such that it's rarely the case that you have an A after a T, and you don't know of really any words that are just T-A-E, tay. And it's rarely the case that you have an H after a C and before a T. And so that top-down expectation allows you to read that as the cat. Sorry, Anna, I missed your question. So would painting bedroom walls blue make it harder to fall asleep, or is that explicitly for light? So it's a good question. The reality is blue is just the reflection of blue light. And so there would have to be some sort of source for that light to be reflecting that blue. And so if you removed all the blue light from an actual like fluorescent bulb, for example, and then projected it into your room with blue walls, your walls wouldn't actually appear blue anymore. And so it's just the reflection of that light emanating from those bulbs. Hopefully that helps. All right, so we have this experience, we have this knowledge, some of which we're born with, some of which we develop over time. And so parts of that information feed into our perception of depth. And so we have these series of cues that we call pictorial cues, because literally you could get the experience of depth in a picture, pictorial picture. One of the clues is the linear perspective, right? This is just suggesting that lines that are parallel appear to converge on a point the further they get off in the distance. This is the effect if you stand on a railroad track and look at that railroad track going off into the horizon, it appears to converge on a single point. Occlusion is essentially just the obstruction of one component behind the other, right? So this tree in the front occludes the tree in the back. So you know this tree in the front is closer than that tree in the back. Same there with the tree in front of the columns. Then you have height and plane, right? So the closer the base of something is to the horizon, more frequently, the further away it is. Light and shadow, so things that project a shadow have a certain orientation, right? So knowing where that sun is coming from to reflect the shadow gives you a representation of the relative positioning of those two objects. Relative and familiar size. So you know, you've got these kind of priors that trees are rarely massively bigger than buildings, right? So your expectation is that it's not the case that this building is really small, it just must be further away. Textural gradients, so things that are up close, you're able to resolve more of the small details, the fine details, than things that are off in the distance. Think about this, of lily pads on a lake. Up close, you can see all the individual lily pads. Further away, the more it looks just like a single conglomeration. Proximity, luminance, covariance. So things that are closer appear brighter than are things that appear further away, right? Because as light is reflected off of the surface, the amount of scattering is directly proportional to the amount of volume between you and that source of reflection. And then atmospheric perspective, or aerial perspective, things that are up close look clear, things that are in the back are a little more hazy. All right, so think about this of walking through fog. When you're walking through fog, you can see things up close really clearly. Things that are off in the distance are a lot harder to see. Yes, those forced perspective rooms, those are awesome. You then have a motion cue, right? Motion parallax. So if you've ever driven alongside a mountain range, it appears that the guardrail right next to you is moving a lot faster than the mountain range off in the distance. Or in this case, Mario, they're giving you the experience and Mario's a lot closer to you than the mountains in the background because of how much faster Mario appears to be moving and the bricks appear to be moving compared to what's off in the back. This is also the principle they use to try to figure out how far away galaxies are in our universe. All right, we're going to skip that one. All right, true or false? Losing one of your eyes means you lose depth perception. False. Yes, this is one of the biggest myths that always irks me. People say, oh, you lose your eye, you can't tell when things are in front or behind something else. Like, well, no, I just showed you a whole bunch of examples of these sort of pictorial cues. Yes, it's true, having two eyes is really good for the very close, but outside of about an arm's reach, having two eyes doesn't really do anything for you.
What about like maybe not depth perception, but like not spacing, but maybe location alignment? That's something you make. It's like you're using one eye, you're kind of offset right, you know. Maybe that's into a location, maybe like kind of.
Yeah, so things that are really close to you, that that sort of binocular rivalry really helps. But if you look off in the distance, that binocular rivalry essentially goes down to zero. And so it is in kind of that parapersonal space, but it's still not preventative of you being able to interact with your environment almost identically to how people with two eyes can. All right. So what about things like visual search? Well, we can classify visual search into two different categories, a serial search and a parallel search. Parallel search is what we also call sometimes pop-out search. So if I said find the red horseshoe, it really doesn't matter whether you're looking at 4 or however many this is. You're able to see it right away, right? It just pops out, assuming you don't have any color deficiency. Your brain is able to essentially search across all in that container and establish what is that target and find it really easily. Conversely, serial search requires you to visit every single point to find what you're looking for. And so how quickly you're able to find that upside down horseshoe is going to depend on how many other horseshoes there are. It's going to be a lot quicker to find it up here than down here, whereas with this parallel search or this pop-out search, it doesn't matter whatsoever. Right, and that's going to matter a lot when we start talking about actual design of systems, how to make displays configured to the user so they can actually pick up on what's going on. All right, before we go into the last little thing here, any questions?
Could you explain that? I mean, I understand the parallel search, but trying to write it down, kind of like,
Yeah.
can you explain that again, the parallel search?
So parallel search we also call pop-out search because the answer just literally pops out to you, right? You have this phenomenological experience. If I say find the red horseshoe, you're going to find it as quick if you've got 4, if you've got 100, you've got 1,000, etc. The answer just boop, pops right out to you, like a flashing light. What it's essentially insinuating is that your brain is able to, in parallel, search every single one of these at the same time and find the right answer. Any other questions so far? Awesome. All right, so let's get into a little bit of the quantification of things here. So one of the best ways we measure performance in visual search tasks is with what we call signal detection theory. Right, and so signal detection theory, we have essentially 4 different quadrants. And they're broken up by the ground truth, the ground state of the world, and then participant responses or user responses. Right? So we're going to call this up here, this signal, this is the ground truth. And the ground truth is that a target can either be present or absent, right? So let's think back to the TSA example. There's either a weapon or there's no weapon. It's present or it's absent. The response on this side is the user's indication of what they see. And they can either respond present or absent. There's a weapon or there's no weapon. When there is a weapon and the participant says there's a weapon or the user says there's a weapon, we call that a hit. When there's no weapon and the user says there's a weapon, we call that a false alarm. When there is a weapon and the user says there is no weapon, we call that a miss. And when there's no weapon and the user says there's no weapon, We call that a correct rejection. And the nice thing about signal detection theory is after we plot our distributions, we're able to get at two different measures. One measure is the discriminability. So essentially, how far apart are these two peaks? That's that D prime measure. The beta is our bias measure. So bias in the response. So you can see the left curve is the noise distribution. The right is the signal distribution. And so let's say everything to the right of that is your yes response, right? And so we have to look in here at that signal and that noise such that as we move this beta around, we are changing the likelihood of getting a hit or a false alarm. And we're able to change that overall criterion based off of what we're interested in, right? Last time we talked about false positives and false negatives, the consequences between those. And so let's again contextualize these hits and false alarms, misses, and correct rejections in terms of type 1 and type 2, right? So type 1 is that false alarm. Type 2 is that miss. And what would we rather prioritize? A type 1 or a type 2 error for TSA screeners? Type 1, yeah, we'd rather them have false alarms. What about finding a date? Would you rather have a false alarm or a miss? Yeah, it kind of depends on how desperate you are, right? Yeah.
I mean, that showed up the date on the only one saying that
Yes. All right, what about seeing a pedestrian while driving? False alarm? Yes. You're much better to slam on the brakes when you don't need to than completely miss it and turn them into a pancake. And then what about picking out the right cup of coffee? Would you rather prioritize a hit or a false alarm or a miss? Probably a miss, right? Yeah. I mean, you don't really want to be drinking a whole bunch of crappy cups of coffee when the alternative is, you just forego a good cup of coffee here and there. And the nice thing about signal detection theory is based off of the responses, we can now plot what's called a ROC curve, or receiver operating characteristic curve, that allows us to quantify what a change in performance does with our bias there. So what you see here on the y-axis is that true positive rate. On the x-axis is that false positive rate. And so let's say we were at 80%. So 80% of the weapons coming through TSA we're detecting. It's 20% we're still not. And so you're brought in to consult because they say, okay, well, that sucks. 1 out of 5 weapons are getting through. And you've plotted this ROC curve, and they say, we want to get to 100% of weapons detected. And you would say, okay, well, we're at 80 here. To get up to 100, we're now going to have damn near a, what, 60% false positive rate. So now, 60% of the bags that don't have weapons are going to have to be pulled out to search for a weapon, right? This is just the trade-off on performance based off of our ability to discriminate between the signal and the noise. And this curve can look very different, right? So you can have curves that look like that represent very poor discriminability. You can also have curves that look like that, represent very good discriminability. So here, on this good discriminability, if we're at 80% and we want to get to 100% detection of weapons, that only constitutes about a 10% increase in false alarms, right? That's not all that costly. Down here, however, for us to even get to 80%, we have to have 60% false alarms. But for us to get to 100, we need to essentially be saying on every bag, yes, there's a weapon, pull it out and search it, right? That's very poor discriminability. The distance between those curves is relatively small. So what can we do? Well, one thing you can do to get the curve looking more like this and less like that one is training. So you can tell people what to look for, right? You can give them a lot of practice. This is what allows Major League Baseball players to see, okay, this is a curveball coming in or a fastball based off of the delivery. When there's not a chance in hell I could tell you what's coming down the pipe. You can also engineer solutions, right? And so one of the things they've done with TSA is give them density scanners, right, in those scanning machines. And so based off of the material density, it gives it different colors. And so now it becomes a lot easier to see, is there a knife? Because you're looking for colors that correspond to the density of metals, right? And so the nice thing with these rock curves is now you can start quantifying what's the actual savings, or what are the costs, right? If we have this initial blue curve, for us to get to 100% detection of weapons, we're going to have to pull out 50% of the bags that come through that don't have weapons. All right, so how many bags go through on a daily basis? Now multiply half of that by, what, 2 minutes to search every bag? That starts giving you a cost associated with increasing that performance. Questions about that? Or anything else we've covered today? Yeah.
For walkthrough, actually, like go inverse, like if they have like really, really bad discriminability.
So it can't go inverse. The worst it can do is just this dotted line, because what that says is it's a coin flip every time. So you're saying for a 1 unit increase in performance or in detecting a weapon, you're having to say, okay, let's just flip a coin.
Or like, for instance, like let's say that, like what would like the curve look like if, for instance, like for the girlfriend example, like let's say I'm a manufacturer's engineer and I'm rich.
Yes.
And like I give you your million and everything.
Exactly.
And now I have a girlfriend. So what I do is I like pull out $1 million and I like start flaunting it.
Yeah, well, so it then depends. You have to kind of establish what are the things that you need to be paying attention to find the person you want to find, right? And so if you want somebody who matches your intellect, maybe it doesn't make sense to, no offense to Tinder, but go on Tinder, right? Right? And so you want, okay, what are the things that you're looking for versus what is your goal, right? And so, you know, maybe without training, maybe you're just kind of throwing it to the wind. Every girl you see, you ask them out on a date, right? Now your discriminability is going to be that 0, right? But you want to say, okay, I want to find the person I want to be with. And so by identifying what are those things you should be looking for, you can now make your discrimination curve look a lot more like this, such that the only people you're taking out on a date are those that have a high likelihood of being a good match for you.
Yeah, but what if the way that you went about trying to select somebody, was selecting the wrong type of person and excluding the right type of person? Would that still just be straight down the middle?
Yes. Yeah. And so, I mean, so if you got to the point where you were only accepting the wrong person and always rejecting the right person, your discrimination curve would actually be up here because you've got perfect discrimination. You're able to tell the wrong person every time and the right person every time. You've just flipped your decision criteria, right? And so the worse you get in that case, the worse you get in terms of your end goal being accomplished, the better your discrimination would be. But to think about you as the worst you could be as a kind of optimal decision maker is for you to be on this dotted line there.
Okay, so after a certain point, it kind of flips over.
Yes. Yeah. I mean, so you can think about the fact that, if you're always making the wrong bet, so you're betting on sports, if you're always making the wrong bet, now just make the opposite of what the initial bet you were going to do is, and then you'll get good, right? You'll get that payout.
That makes sense. Basically saying, if you're betting on sports, you think it's a curveball, the way his hand is, maybe you say, maybe his middle finger is more to the right. I think it's on the curveball, his middle is on fastball. So eventually, every time I bet on that, I'm wrong. But I think it's a curveball, and basically you bet on a fastball. If you know the middle finger is making a fastball, you're just assuming it's something else.
Exactly. You just have to kind of relabel in your mind
basically
that what you're picking up on is. Yeah. Other questions? So Andrew, you can now go through your dating record, plot out the hits, the false alarms, the misses, correct rejections, and establish just how good are you at determining the right significant other.
Yeah, now really good at making the wrong decisions.
Exactly. Yes, sorry, somebody started speaking up.
Yeah, my question was just kind of in a real world scenario. Say you were working in a company or you were doing research for someone. Most of the stuff I would say, and of course, all of my questions kind of lead towards getting a job in UX and stuff like that. Most of the stuff sounds like it's things that might be in the background. Like I don't know that I'd show a bunch of graphs to say a general or a stakeholder. But this is all stuff that once you get into a bottom line scenario where it takes X amount of dollars to get to the goal that you want, you could provide them with that information. And then if they're saying, well, where did you come up with that? You have all of this to back it up to where it's quantifiable. Like this is how much it's going to cost for you to get this good. Do you want to spend the money?
Exactly. Yes, you're exactly right. And so these ROC curves are really great at if you can then start quantifying, okay, what is the unit cost, the personnel cost, the workers' comp cost, et cetera, associated with you being wrong. Now you can say, okay, well, if you are at 80%, if you want to get to 95%, that's great. But this is how much it's going to cost you as a company to get to that 95%. And then here's what that savings for you being at 95% would be. And so you can start weighing that back and forth. Yeah.
Right. Which would depend, especially it's kind of like the old analogy where, having a 1% failure rate if you're a major airline is not good, versus if you're Apple, releasing the new OS.
Exactly. Yeah, you're 100% right. Yeah, so this becomes a nice way to kind of quantify that performance there. Any other questions? Awesome. Well, I'll stick around if anybody has any questions. Remember, on Tuesday, we're having our guest lecture. That will be entirely on Zoom. For those of y'all who normally come on Tuesdays, stay home or just don't come in here. And yeah. Thank you.
Thank you.
Just out of curiosity, is this gets like, or is it a person who's in the psychology field, or is this just yourself, or?
So she actually has her degree in architecture. So she has her degree in architecture, and she,